Okay, so I'm a PhD student here at the University of Northern BC, and trying to finish my PhD up this fall or winter. I work with Dr. Brian Menounos, and I've been working on a project that's funded by the Columbia Basin Trust and BC Hydro, looking at glaciers in the Columbia and Rocky Mountains. So the primary motivations, at least from the funder's point of view for this project, is how fast are the glaciers that were in the Columbia Basin, how fast are they melting, how much runoff do they produce downstream, so both for the Columbia itself and for the smaller rivers that feed into the Columbia, and how much snow actually exists at high elevation. It's something that's not measured in the province. So as a PhD student, I have to ask some novel questions. I can't just go out and do some simple monitoring. Some of the objectives that I wanted to know is, can we look at the balance of these glaciers, how much they're changing seasonally? Can we use LiDAR to do that over larger areas than we can physically do in the field? And are the glaciers that we chose to study, are they representative of the rest of the glaciers in the basin or glaciers near those sites? So the Columbia River Basin in Canada is in southeastern BC, as you can see up here. And this portion, the basin here, we have 6 primary study glaciers with the red stars, from the Zilmer Glacier up near Valemount in the north, the Nordic Glacier and Illicellewaet Glacier, Illicellewaet's in Rogers Pass in Glacier National Park, the Conrad Glacier near Golden on the edge of Bugaboo Provincial Park, the Kokanee Glacier and Kokanee Glacier Provincial Park near Nelson, and the Hague Glacier, which is on the Continental Divide south of Canmore and Banff. So these are our study site glaciers that we chose as a snapshot of the basin for our 5-year project. So to give you a little background on glaciers, glacier mass balance is primarily what we're studying, and that's how much the glaciers gain or lose over a given year. So how much accumulates, how much snow falls during the winter, and how much snow and ice melts during the summer. The sum of that is your annual mass balance. So we have 2 methods which we use to measure mass balance. One is field measurements. This is a snow core. So we take measurements of how much snow falls in the winter, so that's what we're doing here. We're measuring how heavy the snow is, we measure how deep it is, and how dense it is, because snow science and glacier science is all conducted in water equivalent. You know, if you're out for a ski day this winter and you had an awesome powder day, you get face shots, it's blower powder, that doesn't have much water in it. Whereas if you have a heavier snowpack, that has a lot more water. So everything is in terms of water. These are some topo maps of some of the glaciers we work on. The red dots are stakes. Those are basically long poles up to 6 meters long that we drill into the glacier. We use those to measure how much ice melt there is. We take snow depth measurements. We measure how dense the snow is. Those are some of the mass balance measurements that we take. We also collect LiDAR surveys biannually. So when we're doing the field work in the spring, April, May, to measure how much snow accumulated and how much melt occurred by August, September, we collect LiDAR surveys of all of our study sites. This is an example of the detail as you just got from some of the other talks that you can get with LiDAR. We fly at a much lower resolution than for forestry because snow will absorb your signal. It's also more expensive the more points you get. We do about 2 points per square meter on the ground surface, so those are elevation points. This is an example, this is a serac, this is an ice fall up here, basically a broken section of glacier, steep broken section. This is a big serac that fell while we were in the field. And it hit the glacier, and you can see here there's an avalanche crown, so it created a slab avalanche, and then that ice chunk just continued on its merry way, sledding down the glacier. The LiDAR that was flown, it's shown here. You can see that same avalanche debris and then the track of that serac. This is just a fun illustration of the detail that the LiDAR captures. The LiDAR was flown, I forget whether it was 1 or 2 days, whether it was I think it was the day after this incident. This is the terminus, or the toe of the Conrad Glacier in 2014 in September, our first image of the Conrad. And I'd just like to show you the change of the Conrad. And this is 2014, 2016, 2017. So if we flicker between them, you can see the lateral retreat of the glacier. It's shrinking in length, but it's also, you can kind of see the glacier itself deflating a bit, shrinking in thickness as well. So that's a visual of what it looks like. But if we take 2 of these DEMs, or these 3D maps and subtract them. Say we take 2016 and 2017 images and subtract them, we get a height change. On Glacier, we assume that height change is melt, and there's a scale for how much melt we're experiencing on the Conrad Glacier. This is from 2016-17, so you can see at most around 10 meters of melt at the very lowest portion of the glacier. This is just the Tell. Most of the glacier is not depicted here. So that's one thing we can do. We can take a September image from one year and the next and get how much mass the glacier is losing, but we also want to know how much snow is falling both on these glaciers and the surrounding terrain that's just covered by rock or other forests, whatever the land cover may be. So this is the Osola Glacier, this is the Conrad Glacier, and these are winter images. So we've taken a September map and an April or May map, subtracted those, and any height change between the two is snow depth. In the field, we measure the density, or we can use provincial snow density data in the BC Snow Survey, and we can calculate how much this is in water, in terms of water. This is an example, again, this is the glacier we work on, the Conrad. There's many other glaciers around here that we'll talk about later. And this is 2014 to 2017 mass change. So 3 years of annual balance, so subtracting the September 2014, September 2017. So we can see a lot more mass loss down low on the glacier than up higher on the glacier. And then a lot of terrain we also capture that's not glaciated, all this hill-shaded terrain outside that I've clipped. But we use that terrain's valuable for us because we need to tie those DEMs together. They don't necessarily line up perfectly. There might be a shift horizontally of a meter, there might be a shift vertically of a half meter, 20 centimeters, it depends. But we use this stable terrain. We classify terrain off glacier as stable terrain if it meets certain criteria, and we use that to co-register or basically tie together the bare rock surfaces around the glacier so that we know what we're measuring on the glacier is actually due to mass change. You can see some interesting things. This is 2016, 2017, so 1 year's mass change. You can see these really crevassed features. This is the crevasse field where that image of the Sirac Fall was. The blue-red is crevasses moving down glacier. So if you have a really deep, let's say a 15 meter deep crevasse and it moves 50 meters down slope, where it used to be is going to look like it lost a lot of mass. Where it is now is going to look like it gained a lot. That's why you see this messy blue-red pattern here. Those are crevasses moving down glacier. Down here you can see a lake that filled next to a glacier. And we do that over many years, trying to establish kind of a baseline for what's going on with these glaciers and how much water they're contributing. Winter snow density we measure in the field, but when we want to know annual balance, we also classify the surface types of the glacier to know how much water that produces. So ice has a density that's very close to water. Firn, or multi-year snow, if we're losing multi-year snow off the glacier, that has a higher density, and then snow from that given year also has another density. This is the Illicellewaet Glacier. So we classify every pixel as snow, firn, or ice, and then apply that density to any height change. And that will give us how much water that pixel contributed. We just want a total for the glacier. It's a pixel-based classification. So one thing we're trying to do, we can only physically go out there and work on a handful of glaciers. That's hard enough as it is. It takes weeks, usually 4 to 6 weeks for a field season if we're working on all 6 sites. But with the LiDAR, we can collect a lot more glaciers. So here on the y-axis, we have the field data, or the glaciologic mass balance against the geodetic. That's just the LiDAR mass balance, and the 1-to-1 line of summer, annual, and winter balance. And you can see we have really strong agreement between both methods, which is good news for us, but it also means we can kind of scale up what we're doing to say more than just what's happening to those 6 glaciers that we physically visit in the field. This is a given year, looking at winter balance in blue, summer balance in red, and annual, the sum of the two, in black. You can see overall strong agreement. In some cases, there may be a larger disagreement. The different in shading, the darker colors are the field observations, the lighter colors are the LiDAR observations. And you can see that the LiDAR observations, in general, we had pretty good agreement. Sometimes date discrepancy, things like that can lead to differences. or the number of field measurements that were taken, or a storm between the two. There's different factors. So about those other glaciers, we fly Conrad Glacier. Conrad, we study this main branch of the Conrad Glacier. We chose it for accessibility and because within 5 to 10 years, this Conrad Glacier will be 2 glaciers. These halves will separate. So we chose the main stem as our study glacier that we work on in the field. But we also have about 30 glaciers around the Conrad. So looking at those glaciers, how do they compare to our study sites? Well, fortunately, if we look at our study glaciers versus the glaciers around them, we had strong agreement between the two. So that suggests that we can talk about a lot more. We're studying, we capture 100 glaciers every season for snow depth and mass loss versus the 6 that we work on, so a much larger sample size in the basin. We also use our LiDAR data and we use feature tracking. So basically a pixel, a software that looks at the movement of pixels. And so we use our LiDAR data to calculate the velocity of these glaciers. And you can see that the faster parts, this is that ice fall of the Conrad that I showed you a photo of in the Serac fall. So that's a steeper portion of the glacier. That part's moving very fast. It's moving at 50, maybe even 100 meters a year. Whereas other areas, flatter areas of the glacier, more like 30 meters a year. So we're measuring quite a few different things about these glaciers. This is Nordic. Similar story here, slower flow than the Conrad though. So one thing we do is we also measure the thickness of these glaciers. There wasn't any data in the Columbia River Basin about how thick the glaciers are. There were model estimates based on physics of, well, the glacier's this size, it has this slope, so it should be about this thick, but there was no measurements. So we want to know how thick they are, both so we can accurately model them and just so we know what's the reservoir volume of ice in the basin. So this is us hauling a radar system. This radar sends a signal into the glacier, and hopefully we get the strongest signal being where the glacier meets the rock. And that's collected by the front box up here. And that's a familiar face. That's Alex in the back here helping out.
Oh, yeah, that's Alex.
So this is Illecillewaet Glacier, which we measure for parts of Canada. And this is thicknesses across the glacier. You can see the deepest spots around 260 meters thick. But you see this right down the center line, you can see this kind of thicker band of the glacier. And if we look at the velocity map of Illecillewaet Glacier, we see that that thicker portion has faster velocity. And that's because velocity on a glacier is controlled by the slope and the thickness. Thicker glacier flows faster, steeper glacier flows faster. It's just the driving force moving that ice kind of like molasses down the mountainside. So a piece of what we want to do with this work is when we're out in the field, we can go up and measure how the glacier changes with elevation. So up high in the glacier, even in a bad year, typically it will retain some snow. Down low, it will lose a lot. But also ice is flowing downhill. So in the field, any measurement tells you here's how deep the snow is. With the LiDAR, a measurement anywhere on the glacier tells you very little, other than the average is very accurate. So we can average over the whole glacier, because some portion of the height change of every pixel is due to the glacier flowing. So up high on the glacier, most of the velocity is horizontal, but there's a little downward component up high. So the glacier is actually sinking a couple meters a year. It's being replenished by snow, so you wouldn't see that. And down low, the glacier is rising up a couple meters a year. You won't see that because, again, it's being essentially shaved off by melt down low. But that confounds LiDAR measurements. If you looked at these maps of snow depth of the Conrad Glacier and had been there, you'd be surprised that it looks fairly even across the glacier. The glaciers are more even than off-glacier terrain, but actually there's around 5 to 6 meters up high on the Conrad versus 2 to 3 down low on the Conrad. And it doesn't look like it because the glacier is flowing. So our next step of the project is to produce gradients like this of elevation and mass balance from the LiDAR. This is from fieldwork. And this is really what glacier models and hydrologic models need. If you want to predict what's the glacier going to be like in 10 years, 50 years, 100 years, will it be gone, what size will it be, and also how much runoff they produce. Because our glaciers are shrinking, they're retreating, the snow lines are moving up, and so to be able to better predict them, this is the kind of data that we need to be able to put into models and be able to figure out how to manage for when glaciers are either gone from the landscape or far diminished and greatly impacting August and September stream flow and ecosystems which they support. Thank you.
for a couple of questions. Anybody?
How do you get on these trips, Ben? Like if Alex gets all the groovy stuff, right? I have to teach GIS, he does remote. What's going on?
I like to ski and suffer in the cold.
Yeah.
Cracks the whip.
Oh, yeah.
Just a quick question. One of the images you showed at I guess the toe of one of the glaciers, in the third image, there were a few very thick, solid black lines, and I was just wondering if that was, going from one ear to the other. I didn't see those before, if they were just
Oh,
like
those were no data holes.
Okay.
I had been lazy there. There was a lot of forest fire smoke that year, and since it was off, I cleaned a lot of that. You could use a computer to get, but the forest fire smoke was so bad that it took a long time to manually get rid of the smoke in the air. And that was off Glacier, so I just put the hole instead of trying to draw it all out.
Perfect. Thank you.
That's really cool work, Ben. How is this feeding into BC Hydro's models?
So in a couple ways. So basically, this data goes into UVic, or Pacific Institute for Climate. Anyway, at UVic they have a hydrologic model. This data goes directly into their model, especially the balanced gradients. That data goes into their hydrologic model, which is then given to BC Hydro, and then they do their own tuning with that model and run it to predict what stream flows will be like down the line. One of their biggest interests, and something I've been working on the past few weeks, is looking at the off-glacier snow. That's not part of my PhD, but so they really want to know what those gradients are, how much snow is up high, because until last October, all of BC Hydro's automatic snow weather stations that you can go online on the snow online and see the snow pillow sites out there. All those are at tree line, none go above. But now there's one at Conrad Glacier, 2,600 meters. So they're starting to think about looking at those higher elevation snow
Yeah, that's good. I know that they were quite intently looking at snow pillow data for stream flow calculations and annual usage. So this is very good. It's well.
And this works a little bit with Water Survey Canada too. We've installed a stream gauge. This is Nordic Glacier downstream of Nordic and Conrad glaciers. And the Nordic one is live online now, so you can look up Nordic Creek. So starting to figure out how important glaciers are to those streams. And one thing they really want to know about is ice wastage. So that's the unsustainable loss over a given year. So glaciers, there's a lot of snow on the glaciers. And even in a normal year, if you had a zero mass balance, you gain some snow, lose some ice, that would be zero wastage. But in today's climate, we're losing a lot of ice. And it's kind of like drawing down our bank account. So that's a value that they really want to know what's going on.